Hello, I'm Callie Bonzisi, and today I will be talking about the physics behind an inclined plane. So an inclined plane looks like this, and you have a right angle here, and you have theta here, and you have some type of object, we'll just say a ball, going down the inclined plane. And so, before I really get into all the physics behind the inclined plane, I need to explain to you what a force is. So a force is an interaction between two objects, and you have two different types of forces. You have balanced forces and unbalanced forces. So balanced forces are forces that are equal, that means the net force is equal to 0, and unbalanced forces are forces that are not equal and they cause accelerations. So the two type of forces that I'll be focusing on in this inclined plane example are your gravity force and your normal force. And so I will not be talking about friction force because I'm going to assume that this incline here is frictionless, so just forget about friction for this example. So your gravity force, the direction is it goes towards the center of the earth, and when is it present? Anytime two objects have mass. So this is literally always. You could have a gravity force between you and another person and you guys don't have to be in contact. So no contact is not required, and this is the symbol right here, Fg. And so what is normal force? So the direction it occurs, it's perpendicular to the surfaces in contact. And when is it present? When surfaces are in contact, that's the symbol. And as I've said, contact is required for normal force. So now that you know a little bit about the forces, I'm going to get into the physics behind an inclined plane. So I'm just going to open up a new sheet here. So we're going to draw the inclined plane again. So here it is. Angle theta, right angle there, and we'll have a ball coming down the inclined plane. So there are many different forces going on here, and the first thing I'm going to do is I'm going to draw a free body diagram, which is just a diagram that shows all the different forces acting on the object. So this dot here represents the ball, and so you have gravity force, which is always happening towards the center of the earth. So that's going to be your Fg, going right there. This is our Fg. And you also have your normal force, which always happens because the two objects are in contact, the ball and the plane. So, as I said, the normal force happens perpendicular to the objects in contact, so it's going to happen like that, perpendicular. So this will be your Fn. So that's your Fn. So the first thing that we're going to solve for is your gravity force. So Fg equals mg. So what do m and g stand for? M is just mass, and g is gravitational force, which is always 9.8. So Fg is also equal to the mass times 9.8. And through this example, I'm not going to set mass to anything, and I'm not going to set theta to anything. So just when you're actually solving for something, you just plug your mass into m, and you plug your angle into theta. But so I'm just going to refer to it as mg from now on. So this is equal to mg. So when you're looking at these objects, imagine if you had an x, y plane. So the object is rolling down. Nothing about it's going like this. Nothing about it is happening in the y plane. So you know that your y forces have to be equal. So if we kind of broke down the gravity force into an x and a y, so this was your Fgy, and this is your Fgx, you know that your Fgy is going to have to be equal to your Fn since it's not moving in the y-axis. So now I'm going to go over how to solve for that. So again, I'm just going to open a new page here. So here's our inclined plane again. This is theta. This is the ball, and it's going down. And so here's our free body diagram. Gravity, normal force, so this is mg, it's also known as Fg, and this is Fn, and we have this right here, this will be our Fgx, and this is our Fgy, and we know that these two forces are equal, and we also know that this angle right here is theta, and this is a right angle. So here comes in the trigonometry. So what do we have? We have a hypotenuse here that we know, and we also have an angle that we know, so we can solve for these two sides using trigonometry. So you can use your SOHCAHTOA, So we can use SOHCAHTOA to solve for all this. So what do we have? So we're solving for Fgy, so we have this angle, and we have a hypotenuse. We know that the hypotenuse length is m times g. So if we look, that would be our adjacent over our hypotenuse. So the sine of this would give us this over this. I mean, the cosine of this would give us this over this. So if we did cosine of theta, we would get the opposite, we would get the adjacent, over a hypotenuse. And then if we just wanted to get the adjacent side, which is poorly written, so if we just want to get the adjacent side here, all we would do is we multiply by the hypotenuse, and we'd have the adjacent. And the good thing is, we have the hypotenuse. So we can also say that FGY, which would be our adjacent, is equal to mg, which is our hypotenuse right there, times the cosine of theta. So fairly easy to solve for that. And since we know that FGY is equal to Fn, we can also say that Fn is equal to mg times the cosine of theta. So there you have it. You can solve for your FGY and your Fn very easily. So I'm just going to open another new page, and we're going to solve for FGX. So I'm just going to draw this out one more time. That, and you have theta, you have your ball, and it's rolling down. Free body diagram, gravitational force down, normal force perpendicular, Fn, Fg, this is mg. So we have theta, right angle here, this is FGY, this is FGX, and we know this is mg times the cosine of theta, and we know that this is mg times the cosine of theta. So now let's solve for FGX. So your FGX is just going to be the sine. So if we did the sine of theta, so sine of theta would give us opposite over hypotenuse, and the opposite side would be your FGX. And all you'd have to do is multiply by h to get the hypotenuse, and again, we know to get the opposite, and again, we also know the hypotenuse, so we could say that FGX, which is our opposite, is equal to mg times the sine of theta. And there you have it, you also have the FGX. So now, as I was saying earlier, the only plane that the ball will be moving in is the FX, is the x-plane. Because as I said, it's not moving up or down, the ball isn't moving up or down, it's going like this in your x-plane. So we also know that the net force, since again we're not including friction, we know that the net force will also be equal to the FGX, so we can say the F net is also equal to m times g times sine of theta. So now that we have our net force, we can also solve for acceleration. So I'm just going to open a new page again, and here we have our inclined plane, theta, the ball going down. So I'm just going to draw out our free body again. This is your FG, this is your Fn. Break the Fg down. We have FGX and FGY. This is FGX, and this is equal to m times g times cosine of theta. This is mg times cosine of theta. Please excuse my bad handwriting. This is mg, and we also know that fx is equal to m times g times sine of theta. And we also know that our F net is equal to mg times the sine of theta. So the F net is also equal to m times a. So we could just say ma equals mg times the sine of theta. So on each side they have mass, so let's just take out the mass. So we can say that the acceleration is equal to g times sine of theta. And there we have the acceleration. So as this points out, if you have a frictionless plane in an inclined plane, the mass does not affect the acceleration. It's really just the angle that will be affecting your acceleration. So now let's just do an overview of everything that we've just learned. So you have an inclined plane with a right angle here, theta, the ball is going down. Let's draw out a free body diagram once more. gravitational force, normal force, break the gravitational force down. You have theta here, right angle here. This is equal to mg, that's your fg, that's your fn, fgy, fgx. These two are equal, and these both equal mg times the cosine of theta, and fgx is equal to sine of theta, mg times sine of theta. Sorry about that. So we have all this. So let's just write this all out. So we have fn and fgy, since they're equal mg times cosine of theta. And then we have fgx and fnet, since they will be equal in this example without friction, are equal to mg times sine of theta. And our acceleration will just equal g times sine of theta. So there you have it. You can solve for all these different forces and your acceleration just by knowing a few simple things. And so now, if you want to go to my simulation, I think you will be able to understand it more. Basically what you will do is you will choose the angle and the mass, and I will tell you all of this. I will tell you the net force, the normal force, FGY, FGX, Fnet, and I will also tell you the acceleration. And just again to point out, since you are choosing the angle, the acceleration can change, but if you change the mass with the same angle, the acceleration will not change. But I included that in the simulation just so you can see how the mass really does not affect the acceleration if the angle stays the same. So yeah, I hope you understand more about the physics behind an inclined plane, and I hope that the simulation solidifies all of this that I just went over. So thank you for watching, and yeah, go to the simulation please.